What's up to you all matriculants? Welcome to Learn Extra Live. This is Abram and I'm with John today. We're doing physical science, one of your best and most exciting subjects ever.
Absolutely. I'm so geared for this subject this evening. This is a great topic. I don't want you to get nightmares about it. It's definitely not a nightmare topic. It's one that you've got to love, you've got to embrace. It's like a Valentine's Day topic.
Okay.
Just don't turn it into a nightmare, whatever you do.
Nice one. I wonder why Valentine's Day out of all days, but otherwise, what is it all about, John?
Okay, so work energy theorem, it's really practical. The reason I'm saying about nightmares, if you've listened to the other matrics from previous years, I know lots of matrics struggle with this section. But if you get the basics right, you'll love it. And you'll love getting full marks for these problems as well. So let's go right back to the beginning. I know that you've been dealing with energy and work. You've been talking about it probably since about grade 9. Let's make sure we've got the basics in place, and then we'll be ready to challenge and to answer the most difficult challenges.
Does it cover most marks on, is it a bigger section?
Okay, no, it's not a particularly big section, but learners do struggle with it. So it fits together with things like vertical projectile motion, momentum, and then this thing called work energy power. And we're just dealing with the work energy theorem today. Next week we'll carry on and we'll do some power calculations as well.
Awesome. With the same energy I have, my instructors, you stand a chance of winning this awesome calculator. It is a Casio calculator and it is about 254 functions. It's very exciting and it's a must have. Trust me.
And you know what, Abram? Guys, it's the same calculator, or we use the emulator here on the smartboard. So whatever we do here, you'll be able to do on the calculator back at home. So you've got to enter. Don't leave this too late, okay?
So true. And to enter, you simply download the notes or view the notes on the direct links that I'll post on Facebook, facebook.com/learnextra. You know the page. Share the page with all your friends, your classmates, your teachers, and let them like the page and let's engage. But otherwise, there is a form also on the links that I have. That form, it is a form with the test yourself questions whereby you need to give us the right answers. And the first person to give us most right answers before 4 o'clock tomorrow will win this awesome prize. But to talk to me, it's simple. Go to facebook.com/learnextra or on Twitter @learnextra. John?
Okay, guys, I know Abram was rambling there and he was racing. So I'm going to take it slowly now. I want you to get this calculator and I want you to practice the physics too. So how are you going to do it? You're going to go on to use your mobile device, use whatever device you have got, and you're going to go onto the Facebook page. Log on to Facebook, and you'll see a couple of things on Facebook. You'll first of all see the challenge question, and let me just refresh it, so the challenge question will have time to come up. I've just posted it. It's coming. Give it a second. And if you scroll down, you will see that there are links to the Casio calculator competition as well. It is called Test Yourself. Those questions are in the notes that you can download, but we need you to enter. And to enter, there's the challenge question, we'll come to it. We need you to enter. You're going to have to enter on this link here which says to win the calculator. It'll take you to this form. There we go. That is what it will look like. You have to fill in your name. Now, please don't say that your name is Abram and that your phone number is XXX and that your email address is YYY, because then you can't win. We'll get your name and your number and can't win, okay? So you've got to fill in the real thing, and when you click on it, you will see that you have to answer all the questions, and you can go 1, 2, don't let me leave one out. Just tap in the right answers. And there are, for the grade 12s, you know what? I've only given you 5 questions, but they're a little bit tough. So I want you to concentrate, get the right answers, do them as quickly as you can. Then you push submit, and in it goes. And you've answered the question. You've entered into the draw, and you could be the lucky person to win the calculator, thanks to Casio. So it's as easy as that. Now, if you think that's a great prize and you think that it's really worthwhile, why not tell a friend? Be helpful here and tell the friend to go and like our page. And that's the thing that I want you to try and get up to tonight. We're at 671. Now, on the calculator, we calculated earlier in the grade 11 show that it's not that many to get to 75,000. Okay, so at this point, I'm guessing, and Abram, if you'll help me here, we're about, what? 29 away from...
329.
It's 229. Guys, 229. You all know more than 20 friends. Get them to like the page if they haven't liked the page. Let's see what's going to happen when we get to 75,000. I'm sure that we're on track to get to 100,000 one of these days. And then there's going to be some great things happening. So let's push it. Get more people because we want to see better results. We want to see you doing better in your exams. Back at school, we want to push it this term. Guys, don't be distracted by all the holidays and the disruptions. With the elections coming up, you're in grade 12. You've got to put your head down, focus on doing some work, take it seriously. The exam timetable's out. You want to be pushing to get the best possible mark you can. So this evening, what are we doing? We're starting this section where we're going to look at work, energy, power. We've just finished organic chemistry. We're back to physics now. I know some people haven't started this, so I'm going to take it especially slowly. Because you might be falling behind at school. Hope you're not, but you should be into this already. So let's see what we're going to do. We're going to first of all pick it up by revising different types of energy. Hope you know what those are. If you have forgotten, we will remind you. Then we're going to define work. We perhaps haven't defined it formally. We're going to look at the formula. We're going to define what work is. And we're going to discuss the relationship between work and energy in this thing called the work-energy theorem. Now, just because it says theorem, don't go all cold and think that it's difficult. It's not. It's really straightforward. So let's make sure that we've got it sorted out. To get us going and to get our brains thinking, here's the challenge question for today. Now, the challenge question is just to help you have something to think about when we need to go for a break, okay? And it helps you to ask some constructive questions as well. You can post your answers underneath the post on the Facebook page. So what does it say? It starts off by saying a car moves down a hill at constant speed. Is there any work done on the car? Okay, think about it. Read it again. Draw a picture. Talk to a friend about it. Post what you think. Okay? In this case, we're not going to penalize you if you get the wrong answer. In this case, we're friends here together. We want to get the right answer. So, in fact, I'd like to almost say there's no wrong answer. Okay? There's only steps towards getting the right answer. And that's what you've got to understand. That along the way to success, you are going to make mistakes. And every time you make a mistake, it's a stepping stone to the right answer.
Can I just jump in
yeah,
there,
sure.
John? On the challenge question already, I see that there are some answers. Some answers just say yes or no. I think it will be nice if they explain.
Absolutely. We need a full explanation. If you say yes, no, guys, you're going to get minimal marks in the final exam. You need to make sure that you explain why you say there is work or there is no work done on the object. Okay, very important point. Thank you for that. And thanks for those of you that have put the answer. But let's build on it. Let's get the best answer by the end of the show. Okay, AB, let's move on. We're going to start by looking at energy. Now, there are two fundamental types of energy. And I'm going to use my pen as an example because at the moment, this pen is stationed about 1.5 meters above the ground. Okay? If I let it go, which I'm not going to because it's a very expensive pen, it would have the ability to fall. And as it falls, because there's a force acting on it, that there would be a change in energy. So it would change from having what we call potential energy into energy of motion, which we call kinetic energy. So there are two forms: energy as a result of position, and gravitational potential energy. We use this formula: EP equals mgh. Now, if you look in some old exam papers, they sometimes just called that E. Or, sorry, no, they didn't call it E, they called it U, okay, as potential energy. It's the same thing. U is the same as EK. Okay. I like to use subscripts, the mgh here. The mass, G stands for the acceleration due to gravity, and H stands the height. Okay. So if we break that apart, what I hope you can see is the mg part is the same as the force due to gravity, and the H is the same as a height or a change in position. Okay? And we could really even say, because it's vertical, then it would be delta y. So we could rewrite it in terms of that. I just want you to keep that idea in your heads, because we're going to come back to it. There's a force and there's a change in position or a displacement. And that's what potential energy is about, measuring the potential energy. Now, when we get to the next type, we take kinetic energy as the result of the object being in motion. So an object that is stationary, like this one, standing dead still, it has zero kinetic energy. Very important for you to understand it. And although it has potential energy, it has zero kinetic energy. Once it starts falling, oh, excuse me, I've got a tickle in my nose. Once it starts falling, it's losing potential energy and it's gaining kinetic energy. I'm just lowering it down, but it's got some kinetic energy there. Oh, excuse me. I really do apologize for that, but I could feel it coming. There we go. The kinetic energy is given by this formula. EK, or sometimes called K, is equal to half mv squared, where v is the velocity or the speed of the object. Please note that it's squared. When you do the calculation, don't forget to square. Very, very important. Now, in terms of all of this, we recognize there's another term that comes in. We talk about mechanical energy. Mechanical energy is the sum of potential energy and kinetic energy. Add those two together and we get mechanical energy. You need to understand that and understand it very well, because it relates to a very important law. The law of conservation of energy, which says in an isolated system, that is one in which there are no external forces. Isolated. Okay? The total mechanical energy of a system will remain constant. So what we're recognizing is that if we have a different object and we were to drop it falling down to the ground, the only force that's acting on this falling object is the force of gravity, force due to gravity. And as it moves from its position of maximum height down to the ground, what will happen is energy will be transferred from being potential energy to kinetic energy. So that just above the ground, just as it touches the ground, the total amount of kinetic energy will be equal to the potential energy that it had at the start. All the way through, sum of potential and kinetic will be the same. It will be the same all the way through. So halfway down the height, the kinetic energy will equal the potential energy, and at the bottom we'll find that all the energy is now being converted into kinetic energy. The mechanical energy has been conserved. It hasn't gone anywhere else, hasn't been lost. You can't lose, make, or create energy in these simple situations. Okay? So we need to be very clear about that. It's absolutely fundamental and vital that you understand that. Energy is conserved. Now, you'll say to me, but hold on, what happens if it does hit the ground. Well, then there's an external force. There's the force of the ground acting on the object. Or if it was running down a slope and there was friction, it could heat up. And energy is converted into this wasted energy. It's not really lost. It's not usable anymore, but we can include it in this form of energy that is heat, sound, light, and we can no longer use it. So the total energy that I started with isn't available to me for use at the end. We say that those things that reduce the total amount of energy are forces that are non-conservative. Normally, we say that energy is conserved. And give an example of the force due to gravity as a conservative force. That's the force acting on the object, and energy is conserved. But if there were things like friction, and friction is the main one that allows for deformation, or a force that's bumping and twisting and changing the object's motion, like the floor hitting a ball, energy is going to not stay the same. The total amount of mechanical energy will not be the same because it's no longer an isolated system. Okay. Now, having spent some time talking that one through, I want us to get to this idea of work. Because whenever we get a change from potential to kinetic, we need to recognize there are two things involved. And I've illustrated it already. There has to be a force, and there has to be a change in position. And if there is a force and a change in position, then that is a way of changing energy. And we say the thing that allows us to change energy, forms of energy, is called work. We can define work, energy, as the ability to do work, or we can say that work is done when a force causes an object to change position. Very, very straightforward. Now, the formula that we're going to use is W is equal to F times delta X. Usually if it's horizontal, it will be delta X. If it was vertical, it would be delta Y. And then we've introduced another thing here, cos theta. Because we've got two vector quantities, a force and a displacement. They're both vector quantities. We're multiplying them together. Now, normally we can't do that. But for mathematical reasons, we can do it if we include the cos theta. Okay? The cos theta, this is where lots of learners get confused, is simply the angle. The theta there is the angle between the force and the displacement. So we'll come to some serious questions on this, and we'll go over it lots of times. What can those angles be? When can there be work done? Well, I hope you can see that if the angle is at 90 degrees, as an example, what's the cos of 90? Cos of 90 is 0. So when these angles, if the angle is 90 degrees, there would be no work done. But if the angle was 0 or 180 or any other angle in between, we can calculate the components and we can work out the work done. We just need to understand what that theta is all about. Okay, the final thing as we come to the end of this session is to look at this statement of the work energy theorem. It simply says the change in kinetic energy of a system is equal to the sum of the work done, also known as work net, by all types of external forces acting on the system. So work net is the change in kinetic energy, which is just the final kinetic energy minus the initial energy. We're saying work is the transfer of energy from one form to the other. We've gone through our summary. I hope it's very clear. We'll see you after the break for some problems.
Thank you so much, John. And during this break, do the test yourself questions, submit your answers for the awesome prize, which is a Casio calculator. And the challenge question is on Facebook. And lastly, we also have the link to the final exam timetable that John spoke about earlier on. So do check it out. See you. Welcome back, my sisters. Now, earlier on, we told you that you still have got a chance to answer the challenge question, of which you still do. And there's so many answers that are coming through, John. I think the mind sisters are watching and they're participating.
Absolutely. Some great answers. I saw that there were over 100 people that had responded. That's really great. Guys, if you think it's a great question, share it with a friend. Get them to like. I need another 95 likes. Okay.
Awesome.
On the page, just have a look quickly. Look at this. We're at 747,705. So if we can just get, no, it's not 95, it's 195.
95, yes.
195. Sorry, I thought it was more than that. But guys, get busy. Let's get the likes up. We want to get to 75,000. I don't know what the surprise is, what's going to happen at 75, but I'm sure something's in store. It's coming our way. Okay, last thing, just there, because it's on the page. Tafira David Musa, shout out to you. You asked for one. Here it is from me. Okay, now let's get going with some physics. So here we get going. Let's see what it says. A motorbike has a mass of 800 kilograms. And what we're told next is it travels across a smooth horizontal surface at constant velocity of 12 meters per second. The biker applies brakes, which exerts a force of 2,500 newtons on the motorbike, causing it to come to a stop. Question. Let's take them one step at a time, and we're going to answer them as best we can. What was the net work done on the motorbike while traveling at constant velocity? Now, guys, it's a little bit of a trick question, but it's important that we understand it. What it's saying is this: net work is equal to what we know, the change in kinetic energy. Change in kinetic energy, which is equal to the kinetic energy final minus the kinetic energy initial. But please remember what it said in the question was while it was traveling at constant velocity. And in the question, it gave us that the constant velocity is 12 meters per second. So I hope you can see that if we put in here half mv squared final minus half mv squared initial, and we fill in all the numbers. Now, I'm doing this for a particular reason. I want you to see that you substitute everything. And we put it all in, minus half, put them in brackets so it sets out neatly, so the examiner or the marker doesn't get a comma and a dot mixed up. 12 meters per second. Now they can't make a mistake. So what's this value? Half 100 times 800 times 144 minus half 800 times 144. Well, guys, it's 0 because there was no change in kinetic energy. So if you were to do this, it's very important that you show your answer. Can't just say W net equals 0. You've got to put in the values, show it, and say 0 joules. Joule is the unit, the SI unit for energy and for work. They're the same thing in terms of the measurement. Okay, so please be aware that because there was no change in speed, constant velocity means 12 at the beginning, 12 at during, 12 at the end. It's constant. Constant means not changing. So there's no work done. Makes me think a bit about the challenge question. Okay? But don't let me put ideas into your head. You must just think about it. Okay? So, now says to me, what was the net work done on the motorbike while braking? So part B now. Let's pick up the critical information. We were told 12 meters comes to a stop. What's velocity when it comes to a stop? Hey, you got it. V final equals 0 meters per second. So I'm now going to substitute in, do the same calculation, just use a different color, and I'm going to say W net equals the change in kinetic energy, and I'm going to spell it out. It's half mv squared final minus half mv squared initial. Put the subscripts in. Tell the person who's marking your paper what you're doing. Very important. Half, 800. You can even put the half in brackets if you want to. Then the final velocity, 0 squared minus half, 800 times 12 was the initial. Before it started braking, square it. So guys, what are we going to get here? Let's put up our calculator. It will give us the answer for this calculation. So we want 0,5 times 800 times 12 squared. And we get an answer of 5,7,600. 5,7,600. So let me write that down. 5,7,600 joules. But notice I put it in the wrong place, and I just want to move it for a minute. I should have put it there because I don't want to step ahead of myself. I must say a half times 800 times 0 is 0. And then I'm going to subtract that. Just erase a little bit there so you can see that it's clear. And what does this give me? It gives me a negative answer of 5,7,600 joules. It means that the total energy is decreasing because there is this force that is using up energy. Some of that energy has gone into heat and the sound of the squealing of the tires. So they started with a certain amount of energy. Now we've applied a force and it's eating up the energy. So that's why it's negative. The energy has decreased. It had more energy to start with. It's got less energy because of the frictional effects here. Okay. So be very clear about this. We say that the energy, the net work done due to braking was negative 5,760 joules. Okay. The last part of the question says calculate the distance the biker traveled while braking. Now, what's quite interesting here is that what we need to understand, and I just want to pick another color. Let's use that color for the moment, is that if we look at this bike and we recognize that here it is, it was going along, and essentially it was going at, sorry, my bike isn't a very good bike, but something like that, and it was going along at constant velocity. V is constant. Now the only additional force, we're not saying that there were no forces. There was a force from the engine, and there might have been some frictional force, but it was constant. What we're doing is we're saying now, in addition to this force, those other forces together made 0 work. So all the other forces made a combination of 0, because we said that right over here. There was 0 joules. So the only force that is contributing to this net work is the force of the braking. So you must get that very clear. So what we need to recognize is that the object is moving in this direction at 12 meters per second, and the force that we're applying is acting in that direction. continues to move forward. But there's a force, and I think we've said it was 2,000. Let's just get it right. 2,500 newtons. So a force of 2,500 newtons, which is the force of braking, acts on this object in that direction. And so now what I want to do is to work out say to you the following. I'm going to say that the W net that we calculated over here is in fact equal to the work done by braking, because all the other things plus the work done by other forces. But in effect, what we've done is said that this one is negative 5760, this one is W braking, and this one is equal to 0, because we calculated that. So we know that's where we're at. But now I need you to remember our definition of work. So we're going to continue with that just a little bit. We're going to say W braking is equal to the force applied times the change in position times cos theta. Now guys, the bicycle or the motorbike is moving in that direction, from this point to that point. That is delta x. If that's the positive direction, that's the negative direction, they're opposite. So if I've got something going that way and something going that way, what's the angle between them? I hope you can see that these are not in the same direction. The angle between them is 180 degrees. And that's what we're going to substitute in. We're going to say, well, guys, we know that W braking from that example there is minus 57600. We know what the force was, 2500 newtons. Don't need to put the newton in. Delta x, which is the thing we're trying to find, times cos of 180. Now, are we getting there? I hope you can see that we're almost there. If we take cos of 180, let's do this on the calculator. We're going to take our value there, which was negative. We're going to divide by the 500. So we're going to say 57600 divided by, first of all, the force, 2,500. And we're going to say that's equal to this number, 23,0. But I haven't done something. I must still divide by cos 180. Divided by, I'm going to put my cos 180. There we go. And what do you see? It means that delta x comes out over here, because that was negative, negative. It comes out as delta x is 23, because I don't think I put a negative in the original one. It comes out as 23. Be very careful of your signs. 23. Oh, there we go. What's the calculator say? 23,04. 23,04. Now, if this was negative 1, then the negative 1 is going to cancel, so it must be positive 23,04, and I've got it right. So guys, please be very careful of that angle. It's very crucial that you get it right and that you get your signs right. Don't drop off a negative sign there. That negative sign must stay there. This negative will cancel with that negative, gives you the correct displacement. Okay, Abram, we're doing okay?
We're doing okay, John. And on that note, I see you're using a lot of this Casio calculator. Maybe you can show us some tricks there, the ones you enjoy most.
Hey, you know what? I think we'll do them on the way, on the run. So let's just see if we can get another question in before the end of this segment. And I'd like the learners to think about this and see if we can get some stuff going here. Because this is quite a long question, and I'm not sure whether I've got enough time to do it. But I at least want to sketch it for you. Okay, so it says an object is pulled at an angle of 30 degrees to a horizontal surface with a force of 40 newtons. The frictional force experienced by the object is 12 newtons. The object travels a distance of 3 meters under these conditions. And then it says calculate the net work done on the object. Notice here we're given nothing about its kinetic energy. So how are we going to do it? Well, we need to remember what the word net means. W net means, let's take force 1 times the change in position times cos theta plus force 2 times Wx times cos theta plus, and as many as we want. So that's what we've got to do. What forces are acting on this object? Well, you know, what I love to do with these type of questions is I always like to draw a diagram. So I'm going to draw a diagram now. And what I'm going to recognize is if that's the horizontal surface, here is my object. I'm not told what the object looks like. I'm told that there's a force that's applied at 30 degrees to the horizontal. And I think I've got that right. We're told that it's a force of 40 newtons. So there's my applied force. And we are told next that there is a force of friction experienced by the object. So if the applied force is to the right, then the frictional force will oppose the motion, and it will be 12 newtons in the opposite direction. Now, guys, we notice that this object moves a distance or has a change in position under these conditions of 3 meters. So from the starting point to the end point, the delta x is equal to 3 meters. Now, how are we going to do it? Very, very quickly and without too much difficulty. I want you to see that what we're going to do is we're going to first of all calculate W net is equal to the work done by friction, and then add it to the work done by the applied force, the force applied. And we sometimes do that as APP. Now, the frictional force, it's acting in the opposite direction to the force applied. We know that that's the force times the change in position times cos theta. And then this one is the force. This is the frictional force. This is the force applied times the change in position times cos theta. And I think I've just got time to do the substitution. This is 12 newtons times the 3 meters times the cos of what angle? 180 degrees. Plus, now here we go to the next force, which is the force applied. And the force applied in this case was 40 newtons. So it's 40 newtons, also times 3 meters. But now what's the angle here? Guys, the cos angle here is 30 degrees. Okay? So we can simply substitute and put in 30 degrees there. We've got it. We don't have to do complicated, calculate the component, and then you could do, but I'll do it straight like that, and you will get the right answer. Okay, I'm going to do it in the break, use the calculator, and I'll confirm the answer with you afterwards.
Awesome. While John does that, also do the challenge yourself question and also the test yourself questions on the form that is provided in order for you to stand a chance of winning this awesome Casio calculator. See you after the break. Welcome back, Mindsetters. I hope that you've already submitted your answers to the challenge question, and John is going to give us the answer in a bit. And then now we're finishing off that last question.
Okay, let's get to the calculator now for that last question. I've already typed in the values on the calculator, just filling them in, and that was for the 12 times 3 times cos 180. Remember, this is the work done by friction. The reason for the 180 is that the object is moving in that direction. the frictional force always acts against it. And here is the essence of what you need to understand. Friction always opposes motion. Okay? So if an object is moving forward, friction will act in the opposite direction. The angle between the frictional force and the object will usually be 180 degrees. They are opposite each other. When they're the same and in the same direction, then it's going to be 0. In this case, though, we had the 40 newtons moving it through 3 meters, acting at 30 degrees. So when I've plugged that into the calculator, and that's exactly what I've done, so you can see 40 times 3 times cos of 30, because that's the angle between the force and the displacement. It's 30 degrees. And what are we going to find? The answer is going to be a decimal that we can put down as 67,92, and the units here are units of work, so that's joules. So 67,92. 67,92 joules. There we've got it. That's the net work done in moving this object with a force applied at an angle, moving across a smooth surface with some friction. I hope you've got that idea. Let's just see if there's the second part. It says, if it was originally traveling at 1 meter per second, calculate its final velocity after 3 meters. So this begs us to use the work energy theorem. And we're going to say, here's the other application. Work net, which we've just calculated, is going to be equal to the change in kinetic energy. Now, I'm using EK. In the past, you might see it in some textbooks as K, where potential energy, EP, is sometimes referred to as U. But it doesn't matter which one you use, as long as you get them right. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. And we've simply got to substitute. Remember what they said. They want us to calculate the final velocity if the initial velocity, the original velocity, the velocity at the start was 1. So let's substitute the values in. Half mv squared, and that's final, minus half mv squared initial. Now, if I am not mistaken, there is might be a little problem here, but we'll just give the general solution then. What we're wanting to do is to get the final answer for velocity. We know that the work net is 67,92 minus a half. Mass we weren't given, so we don't know what that mass is. I'm just going to keep it as m at the moment. The final velocity is vf squared minus half m, the mass that we wanted, times 1 squared. Guys, I'm going to choose the mass to be 1 kilogram. I wasn't given it in the question, but I'm just going to choose it to make my calculations easier. So I'm going to say half of 1 times V final. Oh, that's a terrible one. Let me correct that. That was supposed to just be a 1 there. So we're going 1 V final squared minus half of 1 times 1. And now we can move things across, and we can say that what we're going to do is multiply everything by, well, let's just take this, do the subtraction. Perhaps just easier to do it on the calculator. So the first thing I'm going to do is I'm going to first of all subtract a half. In fact, I must add a half, not subtract a half. Let me just delete that. I've made a mistake. I'm going to go delete over there. I want to say plus a half, adding a half to both sides. And then I must divide through by a half. And then I'm going to say, what's that answer? And then I'm going to divide both sides by 0, 5, which is this 0, 5 here. I'm dividing through by both sides by that, and I'll get an answer. And then I've got to take the square root. So I'm then going to say square root of my answer equals that. And there I get my final velocity is going to be equal to 11,7. Close enough. 11,70 meters per second. And that's it. Isn't that amazing? Notice that this force has increased the speed. It's accelerated the object, even though there was a frictional force, because there's a net resultant acting on this object. Okay, guys, I think that brings us to the challenge question. Are we ready? Abby?
More than ready, because of the answers that we got.
There are lots of answers.
Lots of them.
Okay. Now, I want us to read the question very carefully. It says, a car moves down a hill. So there's the hill, there's the car, and it's moving down the hill. Okay. So it says at constant speed. Is there any work done on the car? Okay. Now, guys, the question that I'm going to change it around to you is to say, are there any forces? Remember, work is equal to force times the change in position times cos theta. And so the question now becomes, not is there any work done on the car, but are there any forces acting on the car? Do you see there's a difference here? So we know it's constant speed, but we know that if we have to work out all the forces, the question said, was there any work done? And it's very important that you get this. So what do we know? It's moving down the hill. So if it's moving, can we identify at least one force, AB? If it's moving down the hill, what would be acting against it?
If it's moving down,
then what's going to act up? The force of friction.
Friction, yeah.
Okay. Now, the car has mass. Okay? I'm sure you understand this is not a massless car. So the car has mass. And we know that there's a force due to gravity acting on the car that acts vertically downwards. Guys, you've got to realize that there's a component of this force that acts parallel to the plane of the object. So there's a force of gravity acting parallel. So there's the force of gravity parallel to the surface. Now this car isn't just rolling down the hill. Okay? There's the force of gravity, there's the force. There must be the force of the engine, the force that's applied. And I'm guessing that at the same time, this might be, I was going to say a learner driver or a lady, no, it won't say that. There might be the force of the brake. Okay? So once we've added in all these forces, we've got to say to ourselves, yeah, there's the force of friction, the force of brake. What do we know about the magnitude of all these forces? When we add the forces together, the net force, one's up, one's down. The net force is 0. Because the car is not accelerating. Which means the following thing. That I need you to understand. That F net is 0, then W net is going to be F net times delta x times cos theta. And if that's the case, then we're going to say that's 0. But does that mean that there was no work done? There will be no net work done. But yes, there is work done. There's the work done by the force of gravity, parallel. There's the work done by the engine, the force of the engine. There's the work done by the frictional force. There's possibly the work done by the brakes. But all of these, if we add them up, some of them will be negative, some of them will be positive. When we add them up, the net, the total, the resultant will be 0. Okay? So please don't read the question incorrectly. So those of you said that there was no work done, I'll give you a mark because I'll say you presumed that you were talking about network. For those of you who said, yes, there was work done, I'll presume that you were talking about one of these. But the examiner at the end of the year isn't going to be so kind. So please explain your answer and make sure that you understand that, yes, there is work done by gravity. There is work done by friction. There is work done by the engine. There is work done by, could be any other things. Okay? But overall, because it was constant velocity, there was no change in kinetic energy. No change in kinetic energy means work net is 0.
Awesome.
Okay.
And no guesswork, okay?
No guesswork?
Right. Can we just take one question because of
Please,
our
let's
time?
just take some questions.
In number 2, improve your skills. Where does the mass of 1 kg come from?
Okay. Unfortunately, when I copied it down, I didn't put a mass into the question. Okay. So just to show you what it would, I made it M be 1 kg. The question should have had a mass in. Okay. It would have been written down there, but I didn't want to just give a nothing answer.
All right, no problem. But thank you so much, John, and
It's
really
a pleasure.
appreciate it.
Guys, quickly, last thing for tonight. Let's make sure, where are we on our likes? I hope that by tomorrow morning, we can at least say, we're almost there. Are we? Well, we're close.
We're so close.
But what about tomorrow? Guys, life sciences tomorrow, don't forget it. Let's see if we can get to 75.
Thank you so much, John, and thank you, Mindsetters, for tuning in. Really appreciate it. Have a lovely evening, and make sure that you still get your notes if you didn't get them, and work on the questions. We love you. Peace.
Energy and work, you've been talking about it probably since about grade 9. Let's make sure we've got the basics in place, and then we'll be ready to challenge and to answer the most difficult challenges.
Does it cover most marks on, is it a bigger section?
Okay, no, it's not a particularly big section, but learners do struggle with it. So it fits together with things like vertical projectile motion, momentum, and then this thing called work energy power. And we're just dealing with the work energy theorem today. Next week we'll carry on and we'll do some power calculations as well.
Awesome. With the same energy I have, Mindsetters, you stand a chance of winning this awesome calculator. It is a Casio calculator, and it is about 254 functions. It's very exciting, and it's a must-have. Trust me.
And you know what, Abram? Guys, it's the same calculator, or we use the emulator here on the smartboard. So whatever we do here, you'll be able to do on the calculator back at home. So you've got to enter. Don't leave this too late. Okay?
So true. And to enter, you simply download the notes or view the notes on the direct links that I'll post on Facebook, facebook.com/LearnExtra. You know the page. Share the page with all your friends, your classmates, your teachers, and let them like the page, and let's engage. But otherwise, there is a form also on the links that I have. That form, it is a form with the test yourself questions, whereby you need to give us the right answers. And the first person to give us most right answers before 4 o'clock tomorrow will win this awesome prize. But to talk to me, it's simple. Go to facebook.com/LearnExtra or on Twitter @LearnExtra. John?
Okay, guys, I know Abram was rambling there and he was racing. So I'm going to take it slowly now. I want you to get this calculator. And I want you to practice the physics too. So how are you going to do it? You're going to go on to use your mobile device, use whatever device you have got, and you're going to go onto the Facebook page. Log on to Facebook, and you'll see a couple of things on Facebook. You'll first of all see the challenge question. And let me just refresh it. So the challenge question will have time to come up. I've just posted it. It's coming. Give it a second. And if you scroll down, you will see that there are links to the Casio calculator competition as well. It is called Test Yourself. To the draw, and you could be the lucky person to win the calculator, thanks to Casio. So it's as easy as that. Now, if you think that's a great prize and you think that it's really worthwhile, why not tell a friend? Be helpful here and tell the friend to go and like our page. And that's the thing that I want you to try and get up to tonight. We're at 671. Now, on the calculator, we calculated earlier in the grade 11 show that it's not that many to get to 75,000. Okay, so at this point, I'm guessing, and Abram, if you'll help me here, we're about what? 29 away from
329.
It's 229. Guys, 229. You all know more than 20 friends. Get them to like the page if they haven't liked the page. Let's see what's going to happen when we get to 75,000. I'm sure that we're on track to get to 100,000 one of these days. And then there's going to be some great things happening. So let's push it. Get more people, because we want to see better results. We want to see you doing better in your exams. Back at school, we want to... Those questions are in the notes that you can download. But we need you to enter. And to enter, there's the challenge question. We'll come to it. We need you to enter. You're going to have to enter on this link here, which says to win the calculator. It'll take you to this form. There we go. That is what it will look like. You have to fill in your name. Now, please don't say that your name is Abram and that your phone number is XXX and that your email address is YYY, because then you can't win. We'll get your name and your number and can't win. Okay? So you've got to fill in the real thing. And when you click on it, you will see that you have to answer all the questions. And you can go 1, 2, don't let me leave one out. Just tap in the right answers. And there are, for the grade 12s, you know what? I've only given you 5 questions, but they're a little bit tough. So I want you to concentrate, get the right answers, do them as quickly as you can. Then you push submit, and in it goes. And you've answered the question. You've entered in.
Hey, what's up to you all matriculants? Welcome to Learn Extra Live. This is Abram and I'm with John today. We're doing physical science, one of your best and most exciting subjects ever.
Absolutely. I'm so geared for this subject this evening. This is a great topic. I don't want you to get nightmares about it. It's definitely not a nightmare topic. It's one that you've got to love, you've got to embrace. It's like a Valentine's Day topic.
Okay.
Just don't turn it into a nightmare, whatever you do.
Nice one. I wonder why Valentine's Day out of all days, but otherwise, what is it all about, John?
Okay, so work energy theorem, it's really practical. The reason I'm saying about nightmares, if you've listened to the other matrics from previous years, I know lots of matrics struggle with this section. But if you get the basics right, you'll love it. And you'll love getting full marks for these problems as well. So let's go right back to the beginning. I know that you've been dealing with